This is what we're going to be doing is starting a new technique today called binary space partitioning, and this continues in the notes on page 39. Okay, so just to sort of recap where we're up to last week, okay, we started the idea of hidden surface removal. So up until now, all the stuff you've been doing last term involved generating your objects, moving your objects into the virtual world. You will then align the virtual world in the direction the viewer is looking at, and you can project that onto a viewing plane or a projection plane, so we can have a perspective view of the world. And early this term, a few weeks ago, we looked at clipping. So clipping is all about removing anything which is outside of our field of view. So if you notice here, these houses on the left, they've been clipped to the screen space. Okay, and that's what assignment 7 was all about. So last week we looked at this idea. Okay, this is what we refer to as a wireframe view. In other words, we've only got the outline of our objects, and our objects appear to be transparent. Okay, well that's not particularly realistic. So hidden surface removal does this step. Okay, it attempts to remove all of those parts of the object which you shouldn't see, because in real life, when things are opaque, you can't see through them. We can't see what's behind that house, for example. Okay, so this is what we're concerned with. Okay, removing of hidden surfaces. And last week we looked at 3 methods: backface culling, painters, and Z buffer. Okay. So I'm just going to do a quick recap of these 3 methods. Okay, this was backface culling. And essentially, all you do is you take each polygon and you check whether the polygon is facing the viewer. And by facing, I mean the normal to that polygon is pointing in the direction of the viewer. If it is, we plot it. If it's not, i.e. we say it's back-facing, we ignore it. So it is a cull of all those back-facing polygons. How do we tell whether a polygon is front or back-facing? Well, it's quite simply dot product. The V is a vector from the camera or from the viewer to the center of each polygon. So for each polygon, we're going to have a different V vector. The N is the normal vector for that polygon. We simply dot product them together. If the result is a negative number, that polygon is front facing. Else, if the result of the dot product is a positive number, we say it's back facing. Okay, and this is what the effect has. So this is the teapot, this is assignment 8, and I may, in the second half of the lecture, I'll go through, give you a bit of tips on this one. Okay, on the left, we have Newell's teapot, or the Utah teapot, with all polygons drawn. Okay, so if I was to rotate that teapot around, you'd see all of the polygons. On the right, what I've done is, assuming a viewer is sort of somewhere from the left, I've only plotted the front-facing polygons. So you can see there's nothing on the back face, nothing on the reverse side of the teapot. Okay, so that's effective backface culling. Okay, so that's just one of the methods we can use to remove hidden surfaces. Okay, well, backface culling, it works. It's especially good when you've got an object which encloses an area, so barrels or a ball or any small object. It's not so good when we view all of the virtual world or all of the objects in a virtual world. So on the left, this graph or this plot here shows my virtual world with backface culling applied. But it looks sort of solid. Each object looks solid, but we've got, for example, this sort of church object here is overlapping this house object, which should be in front of it. Okay, so it works, but we still need to do some things to it. This is where Painter's algorithm comes in. Quite simply, Painter's algorithm sorts all the polygons in descending order of distance. So So if you're looking down the Z direction, as we are after we've aligned our world space, the Z coordinate gives us what's the distance of each point from our viewer. And what you do is you take each polygon, each vertex of each polygon, look for the smallest Z distance, and then you sort all the polygons in descending order of that Z coordinate. Okay, and you plot them in that order. So the furthest polygon away is plotted first, the next furthest is plotted next, etc. So what that does is any polygons which are plotted later in the algorithm obscure any polygons plotted previously to that. Okay, so in the end, we end up with a proper rendering of our virtual world. So it's quite simple. Start at the back, end up at the front. Okay, we also looked at what we call the Z buffer. Z buffer is the same sort of concept, but instead of looking at a polygon by polygon basis, it looks at a pixel by pixel basis. So what we have is a Z buffer. For each pixel in our display, we have a value in the Z buffer. So the Z buffer will be the same size as your screen, or have the same number of elements as pixels in your screen. And the Z buffer contains numbers. Now those numbers are the distance to the nearest surface for that pixel. So what we do is for each polygon, we look at all the pixels in that polygon, we calculate the distance to those pixels. If that distance is less than the corresponding number already in the Z buffer, we replace it. So it's a similar type of process to Painter's algorithm, but just on a pixel by pixel rather than polygon by polygon. If we do replace a number in our Z buffer, we have an equivalent sized another array called a frame buffer where we replace the color. So once you've done all polygons, your frame buffer contains the colors which you then plot onto the display. Okay, so that's a Z buffer. So those three techniques are what we looked at last week. Today, with binary space partitioning, we're going to look at the final hidden surface removal technique. Now this technique requires no, well, the way I'm going to do it requires no calculation. Okay? It's purely sort of in a theoretical approach. And likewise, the assignment 9, which is on binary space partitioning, there's no programming involved, it's purely pen and paper work. And it's a very nice, elegant solution. A bit of history behind this. Anybody ever heard of the computer game Doom? Doom, yeah. Sort of in 94, I think it was, ID Software. Michael Abrash and John Carmack, who wrote Doom, invented this method. And it's pretty much used in any computer game since. It's very elegant. It's very clever. Okay. And this overcomes a problem that Painter's algorithm has. When we have overlapping polygons, so in certain cases you'll have a polygon which is under one polygon but over another. Okay. We need to split up the polygon. Now Painter's algorithm can't do that. Binary space partitioning can. It's a rather posh name, binary space partitioning. Okay, often referred to as BSP. Okay, what does binary mean? Anybody tell me what does bi mean? 2. So we got 2 space partitioning. What does partitioning mean? When we partition something, what do we do to it? Separate, yeah. We split it up. Okay, so all this means is we split up a space into 2. Okay, that's what BSP means, splitting up the space into 2. This method, it determines which polygons need to be split. And what's more is once you do the method, okay, so when you apply binary space partitioning, we record what we do in something called a BSP tree. Okay, so once you've done the method, this tree is applicable from any viewing angle. So what we can say is this BSP tree can be pre-calculated as soon as you draw the virtual world, and then as you're sort of moving the camera around the virtual world, or you're going through it, or you're playing the game, you don't need to have to regenerate the BSP tree. So as soon as you got your virtual world, you generate the BSP tree, and then that's it. Okay, you don't have to redo it again. Whereas the other methods, you have to keep, for every step, every sort of frame, you'd have to recalculate them all. And what we do is we use what we call a tree walk to determine the rendering order. And this gives you the same order as Painter's algorithm, but without having to calculate the distance to a polygon. It's a really, really nice, elegant method. Okay. I'm going to start with a few definitions. These are on page 40. The reason why I'm going to do this is because this is the words I'm going to use to explain the method. And the first definition is a convex set. Okay, a convex set is a set of polygons. Well, in this case, it's a set of polygons that are all facing each other. So every polygon in a convex set is facing each other. So imagine you're a polygon. Okay, your front face is the space in front of you. The back face is the space behind you. If you're in a group of other polygons, i.e. other people, if you can see everyone's front face, you're all in a convex set. If one of those polygons you can see the back face of, it's not a convex set. So for example, on the left, we have a convex set. Set of two polygons, they're both facing each other. Okay. On the right, if just one polygon is facing the back of another polygon, it's not a convex set. Okay, so that's what I mean by convex set. Why is that important with regards to binary space? With regards to hidden surface removal? Well, if you have a convex set, none of those polygons are going to overlap each other. None of them are going to be in front of each other. So if you've got a set of polygons which are convex, you can just plot all the polygons at the same time. You don't have to sort of work out any ordering. Okay, so that's what we mean by a convex set. They're just facing each other. Another rather grandiose term is this term down here, atomic subspace. This is quite simply a subspace where all polygons within that space are convex or belong to a convex set. So convex set, polygons are facing each other. Atomic subspace is a space that contains a convex set. Okay, hyperplane. This is my favourite term because it sounds sort of almost science fiction-y. Okay, a hyperplane is well, the official definition is if you have an n-dimensional space, a hyperplane is an n-1 dimensional object which bisects, which cuts that space to form two new spaces. So, for example, if you had a 3D space, which obviously most of our virtual worlds will be 3D, a hyperplane is a two-dimensional plane. So 3 dimensions, n-1 is 2 dimensions. And what we do is we cut our 3D space by putting a hyperplane through it. Think of a guillotine. Think of just a big cut right through your space, and you end up with two subspaces. And that's what we mean by hyperplane. Okay, so we have convex sets, and we have hyperplanes. Okay, the last thing I'm going to look at or define is the idea of a binary tree. Now, as we said earlier, bi means two. So a binary tree is a tree structure where each node has at most 2 nodes coming from it. So we can't have more than 2 nodes. Okay, so a binary tree, for example, this one on the right, consists of nodes, which are the circles, and branches, which are the lines joining the circles. Okay. So binary tree means each node has at most 2 branches stemming from it. It could just have one. A node could just have 1 branch stemming from it, or like, for example, node D could have no branches, but it can't have more than 2. So nodes that attach to branches of another node are called child nodes. So in this case, B is a child node of A. Okay, so A has 2 branches stemming from it, B and C. So B and C a child node of A. And also we refer to B and C as being sibling nodes. So think of a family tree. Okay, and so B is a child node of A, therefore A is a parent node of B. Okay, you could even take that further. D is a child node of B, so D is a grandchild node of A. It's like a family tree. Okay, a node without a parent node is called the root node. So in this case, our node A is the root node. And a node without any child nodes is called a leaf node. So D, E, F, and G are all leaf nodes. Okay, so this is a binary tree. And what we're going to do is we're going to apply what we call the binary space partitioning process. And we're going to record that process in a binary tree. So we're going to record it in what's called a BSP tree. And that's pretty much that slide saying what I just explained. Okay, so if you have a look on page 41, you'll see the algorithm. Now, as you've seen in previous lectures, this is sort of the formal way in which we present an algorithm. It's just a series of steps. Okay. This one is fairly complicated. Okay, and it's what we call a recursive algorithm. Okay, so if you see at the top, I have a function, and I've called my function BSP tree generation. Okay, that's the name of my function. As you see, within the function, it calls itself. It's called a recursive call. So what we do is we start with a set of polygons S. So let's say we have a virtual world, we've done all the alignment, blah, 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 blah. Okay, actually, we haven't done the alignment. This is before any alignment's done. This is when we've got our virtual world, so all of our polygons. Okay, that's S. So S is a set of polygons. If S is convex, then we don't need to go any further. That's it. We can just plot them. But obviously, if you're going to have a complicated virtual world, it's very, very rarely going to be convex. Okay. So what we do is we choose one of the polygons in our set S, and we insert a hyperplane along it. So we choose that polygon, and we cut through our virtual world. So that's going to split our virtual world into two subspaces. The space in front of our polygon H, and the space behind. Okay, so then what we do, so for all of the polygons in S, except for the one which we just used to split it up, if our polygon is in front of H, then we add it to the left child node. Okay, so if you remember a binary tree has got two children. Okay, so when you split the space up, any polygons which are in front of the polygon which you used to insert a hyperplane along, you list in the left child node. Okay. Any polygon which is behind your hyperplane, you put in the right child node. Okay, so let's say you've chosen one node, you've got maybe thousands of nodes, you've chosen one node, whack a hyperplane along it, all those polygons in front get listed in the left node, all those polygons behind get listed in the right node. Then you do exactly the same with each child. Okay, it's a recursive call. You may have to do this many, many times. Well, actually, in practical reasons, a computer would do it. But in theory, you'd have to do this many, many times. Once you get down to an atomic subspace, so once you get down to when all of your sets are convex, then you're finished with that particular call. Okay. Now, in presenting an algorithm in this way, it's quite hard to actually sort of understand. So it's much better to have a look at sort of examples. Okay, so here I've got a very simple space. It's a space with just three polygons in it, A, B, and C. And you can see I've got their normal vectors showing which side they're facing. Okay, well, if I choose A as the root node, that's the node I'm going to use, that's the polygon I'm using to insert the hyperplane along, it's cut the space into the left, well, the back side, or the back facing side, and the front facing side. So B is in the front subspace, so that gets listed in the left node. C is in the right subspace, so that gets listed in the right node. Okay, so that's my BSP tree for that very, very simple space. Okay, sometimes we'll have what we call coincident polygons. Now, a coincident polygon is where two or more polygons exist on the same plane and they have the normal vectors pointing in the same direction. So in this case, A and B point in the same direction and they exist on the same plane, so they're coincident. What we can do, it's actually preferred, if we can have coincident polygons, it's preferred, is we can list them in the same node. So if I put a hyperplane along A and B, okay, I can treat it as just one polygon. So we have AB, and the front space is the top, or the top portion, which has polygon C, and the back space is the bottom area, and that contains polygon D. Okay, so coincident polygons are just treated as one. So if we can put a hyperplane along two or more polygons, it's often preferable to do so. Okay, so I'm going to go through just a quick worked example. Okay, here I've got 4 polygons in my space, A, B, C, D. Again, I've got the normal vectors. Okay, so let's give it a go. In this particular example, I've chosen C to be my first hyperplane. Okay, so we put a cut down polygon C, and therefore I've listed polygons A and B are in the back subspace, and D is in the front subspace. So D goes on the left child node, and A and B go in the right child node. And you may notice something about this tree here is I've used a square for the AB node and a circle for the D node. Now, the reason behind that is what I tend to do. Now, this isn't sort of, if you don't do this, it's not wrong, but it just helps you to keep track of what you're doing. Is if you have an atomic subspace, I use a circle. So, for example, D is on its own in that front space. So any polygon on its own must form a convex set because it's not looking at the back of any other polygon. So therefore D, I use a circle for the node. A and B are sort of facing away from each other. Okay, so that's not a convex set. So what I've done, and this is, like I say, this is just what I do as a personal thing, but it does help when you're working things out, is I've used a square or a rectangle to denote polygon B. Sorry, to denote the space with A and B in it. Okay, so at the moment, I've still got work to do because I only stop when all of my nodes in my tree contain convex sets. So this node here doesn't contain a convex set, so I've still got work to do. So what I've got to do is I've got to choose either A or B to insert a hyperplane along. Okay, and what I'm going to do, which may seem a bit odd, but I'll explain why in a second, I'm going to insert a hyperplane along polygon B. Okay. So I've cut that back subspace from C into 2. So I've inserted a hyperplane along polygon B. Notice it stops at this point here because as far as this hyperplane is concerned, this space doesn't exist. I'm only concerned with this back subspace from C. So if I insert a hyperplane along B, okay, what it actually has the effect of in this case is it cuts A into 2. Okay, so I've called one polygon which is caused by the cut in A1, and I've called the other one A2. As long as you label it, I could have labelled it E, A and E or something, but A1 or A2, it doesn't really matter, as long as you label it something different. So this has now cut A into two, and A1, polygon A1 is in the front subspace of B, polygon A2 is in the back subspace of B. Okay, A1 and A2 are on their own, so they must be convex sets. And if you notice, all of my nodes now contain convex sets, so I'm finished. Okay, so that is the BSP tree for that, I say, collection of polygons. In that case, it was a very, very sort of simple virtual world. In more complicated cases, for example, computer games, you'd have thousands of polygons. So you'd write a computer program to do all this. In this course, we're not going to be concerned with writing a computer program to do this. We're just going to do it via pen and paper. Okay. Right, so what I want you to do is have a look at, I think I gave out at the beginning some activity sheets. Anybody not got one of these? Hand up, Anybody not got one of these yet? Right. Just doing it so you can see what I'm working out. Okay, so this is the activity sheet you've got. Now, what you've got to try and do is you've got to try and imagine that this is a virtual world. Okay, so what we have here is a kind of plan view of a computer game. Now, I know it's only very, very simple, but you know, we can't go too complicated because we're doing this by hand. So imagine these are like 3 rooms in a computer game, and it's plan view, you're looking down on it. So your character can be here and sort of walk around in the interior of these rooms. Okay, and I've got a number of polygons, and I've labelled them A through to T. Now what you've got to imagine is each of these polygons have a normal vector facing the interior of each of those rooms. So for example, A would have a normal vector facing up, so facing to the right, T would have a normal vector facing up, etc. Okay, so if I put all the normal vectors on it, then it starts to look very complicated, and I didn't want to do that. Okay, so we now have this sort of virtual world. So what we're going to do is we're going to generate a BSP tree from this virtual world, or for this virtual world. Okay, so first things we've got to do is we've got to determine or decide which polygons to insert a hyperplane along. So we're going to cut up our world space into 2. Anybody suggest polygon to use? Doesn't mean there's no wrong answer. There's one that I know what I want to use, but I'm asking you. What was that? What T? TPH, exactly. I was hoping you'd say that. That's what I wanted to do. Okay, so what I'm going to do is I'm going to set a polygon down TPH. So I'm sort of like going to somehow sort of show that. Just going to label out what I want. Okay, and so what we have is we have TPH. Okay, so we got TPH. We could use TP and H because they're all coincident. TPH all lie on the same plane, and they all their normals face in the same direction. Right. So what I now do is in the left child node. I'm going to list all the polygons which are in front of TPH. So we've got A, B, C, D, E, F, G. So I've got all of those around there. Then I've got Q, R, and S. And as I mentioned earlier, I tend to use a rectangle to denote a non-convex set. So this is non-convex, so for example, C and E facing away from each other. Okay, so that's the front subspace. The back subspace are all of those polygons behind. So what we've got, I, J, K, L, M, N, O. Right, so that's my first cut. That's my first. As you can see, it's dead easy, this. Okay, second cut. What I'm going to do is I'm going to concentrate on the front subspace. That's a bit above my first hyperplane. So now I need another hyperplane to insert along any polygon in this group. So pick a polygon out of this group and insert a hyperplane along it. So which one should I use? Or give me one. Again, no wrong answer. Sorry? C? Yes. Why not? So I'm going to set hyperplane on C, and I can also include S in that. So I can also include S because C and S are coincident. So my second one, I'm going to have C and S. Okay, in the left child node, so we've got C and S, they're both facing to the left. So in front, I've got A and B. What can you tell me about A and B? They're convex. A and B, they're facing each other. Okay, imagine sort of, I'm facing this way and you guys over there, we're sort of facing each other. And you guys will be my back subspace. But A and B are facing each other, so they're convex. So I'm going to use a circle to denote that node. The other side is non-convex, so because, for example, D and E are facing away from each other. Okay, so I've got D, E, F, G, Q, and R. I use a square just to denote that that's non-convex. Okay, so I don't need to bother with this sort of subspace up here because A and B are already convex. So I'm going to have to pick one of D, E, F, G, Q, and R to split up this one. So what would be the obvious choice? It would be E and Q, wouldn't it? So I'm going to split up E and Q. That's going to be my third splitting. Now, in front of E and Q, now E and Q both facing to the right, I've got F and G. Okay, F and G are convex. Okay, so I represent that using a circle. Okay, and D and R are also facing each other. So D and R are convex. Okay, so that's sort of all of the space in front of my first split is now done. Okay, so I took this node here, split it along C and S, which gave me this tree. And then I took this node, split it along E and Q, and that gave me the third tree. Okay, so now I'm going to have to go back to this node. Okay, so this is all of this region behind. So what's an obvious splitting for that region? NJ. Yep, NJ. So my fourth hyperplane is going to be along NJ. So we have NJ, In front, because N and J are facing down, I have KLM, they're all facing each other. And behind I've got I and O, they're facing each other. Oops, sorry about that. Just I'll zoom out a bit. Right. All of my subspaces contain convex sets. Okay, so I'm finished. That's it. Don't need to do any more. All I now need to do is put my whole BSP tree together. Okay, so I started, my first cut was TPH. My second cut, which was in the front subspace, was CS. Now, in front of CS, I had AB, which is convex. Okay, so TPH to start with. Okay, and in front of TPH, I had all these polygons. So then I chose C and S, or we chose C and S. That was my next hyperplane. In front of C and S, I had A and B. But behind CS, I had this non-convex set. So I chose, or we chose E and Q. Okay, so to the right of CS, we've got EQ. Okay, and EQ resulted in F and G being in front of it. And behind it, we have D and R. So all I'm doing is just putting all of the separate trees together. Okay, to the right. Okay, what did I do to the right? We chose N and J. And NJ, in front of NJ was KLM, which is a convex set. And behind NJ was IO, which is also convex. And that's a complete tree. That's binary space partitioning. It's easy as that. No, there is no wrong answer. So whatever polygon you pick, it's just that polygon. So I could have started, let's say I started with splitting along L. Okay, if my first split was along L, all the other polygons are in front of it, so they just be in the left child node. Okay, it doesn't matter, well, I say it doesn't matter. It's not wrong to pick different polygons from what I've done, or what we did. For example, I could have picked EQM to start with. Okay, as long as you proceed in the same method, you'll have a correct BSP tree, but it will just not look like that. Which actually makes these sort of exam questions a nightmare to mark, because there are quite a few combinations of BSP trees which could result in that level, or that map. Okay, if you turn over the page, what I want you to do, I've got a slightly more complicated one over the page. Okay, I want you to have a go at this one. Now, this one is not possible to do without splitting a polygon atom. Okay, so it's going to result in a splitting. It's not possible to avoid that. So I want to see how many different sort of ones you do. So I'm not going to tell you how to do it. I want you to do it. But actually, I'll give you about 5 or 10 minutes to do that, and then I'll do mine.
Yeah.
Remember, all of these sort of polygons assume that the normal vector space into the middle of the rooms. We've got like a little corridor here, little few rooms.
do it in the chair.
I'm gonna say this one.
You're not a child.
It's the same name as this.
Yeah, that's my neighbour. There's many neighbours. Yeah, all the reasons. I've worked on it. Ah, it's very good. I will just review A and then when we read that, inside of A. I see. Oh, I don't know. Right. Is it not how we do it? Oh, I did. I did it across there. But I don't want to do this one. I don't want to do that. Can I go and do that bit and then come back to this one? Is that not mine? I've already sliced and now I'm slicing this. I've sliced this way, so I'll just put this bit here. What I'm doing so I'll go to the end of June. Is that written as well? So I literally just did just being kind of over there. That makes it easy.
Okay, I made a couple of mistakes doing mine, but managed to get there in the end. Okay, you will probably have a different one to mine because I tried to pick non-obvious hyperplanes. I wanted mine to be different from yours. So just sort of made the point that just because I picked different hyperplanes doesn't mean yours is wrong and mine's right. Okay. But I'm just going to talk you through my solution. Okay, so this is the, I actually made a mistake a couple of times, but this is the thing. My first cut was down X, D and H. Okay, so all of the ones below that are in front, and all the ones above are behind. Okay, so my first cut was XDH, these are all in front, those are behind. Okay, so looking at the front subspace, I then did EMQ, which is down there. So all these ones, this is the front space, this is the back space. Okay. So then in front of EMQ, I did TP. Okay, so QRS. Oh, hang on, Q doesn't need to be there. Told you I made mistakes. So TP, that's just R and S. Okay, very easy to do. So because Q was already accounted for there, okay, I shouldn't have had it in there. So that was one mistake. So R and S are convex, okay, but the NOUVW arms. So we've got NOUVW arms. So then I split one down NV. Okay, so that's NV. So W's in front of NV, OU are behind. So that's, I've done all of the bottom subspace. Now up here, you can't avoid a splitting. Okay, it's just unavoidable. So I chose AA as one of my cuts. That splits B into two. Now I just labelled them B1 and B2. So in front of AA is A and B2, which are convex. Behind is B1, C, Y and Z. Okay, which is so B1, C, Y, Z. Okay, so now I've got this space. So B1, C, Y, Z. I'm going to have another splitting. It's unavoidable. So I chose B1 to go down there. So Y1, Z is in front of B1. I split Y into Y1 and Y2. So Y1, Z are in front. C, Y2 is behind. They're all convex. At this step, I thought I'd finished, but I forgot about these down here. So I did a split down GK, and IJ is in front, FL behind. Okay. Put it all together. Okay, that's our binary tree. Yours may be different. I expect it to be different because I deliberately chose sort of weird splittings there just to sort of be different. Okay, so that's generation of BSP tree. You will make mistakes, as you saw. I've been doing this for a number of years now, and I made this mistake with the queue. Okay, I shouldn't have had a queue there. I also forgot about GK. So it just comes with practice. I mean, it's quite a simple process. Insert the hyperplane, split it into two. You've got your front space, your back space. Keep splitting until all your nodes are convex. Okay. And that's your BSP tree. How are you finding that? Is that all right? I mean, it's not too difficult. If you were to program this in your computer, how would you know whether something's in front or behind? So, for example, if I had those two polygons are facing each other, aren't they? Well, if I was to take that normal vector and put it here, what's that angle? What can you tell me about that angle? It's obtuse, so therefore it's greater than 90. So let's say that's dot product, that's N1, and that's N2. That's N2, and that's N1. If I dot product those two normal vectors, and it's less than 0, it means what those two polygons are facing each other. If I dot product them and then it's greater than 0, they're facing away. So it's simple dot products. To work out splitting, you have to calculate intersection between a plane and a polygon. Okay, and that's what you did with Killian last term. So intersection splitting is slightly more complicated, but whether polygons are convex is just a dot product. Okay, so it's a fairly simple process. Now, how the hell do we go from that to some form of hidden surface removal? Okay, what we've done is very abstract. Okay, so what we're going to look at now is how we go from the BSP tree to hidden surface removal. Now, this is quite clever. I really like this. Hopefully, you'll like it as well. Oh, sorry, getting ahead of myself. Before we do that, let's talk about optimal BSP trees. Now, as I keep mentioning, you've probably got a different tree than I have, and you may have a different one to your neighbours. Okay, doesn't mean they're wrong. They all can be right, but we can have what we call optimal and suboptimal. And there are two criteria for determining whether something's optimal or not. One is the number of polygons. Now, as we saw in that last example, sometimes splitting is inevitable. We can't avoid it, especially in sort of complicated, large virtual worlds. So when we split a polygon, we split it into two. More polygons means more work. A poor choice of the root node will result in a growth factor of up to 2 to the power n, where n is the number of polygons. So if you started with 10 polygons and you chose really poorly, or worst case scenario, 2 to the n would be 1,024 polygons you could end up with. Okay. So your number of polygons grows with the number of splittings. That's the first criteria, how many polygons we end up with. The second is whether we have a balanced tree or not. And I'll mention what a balanced tree is in a minute. If a tree is balanced, it's more efficient to traverse. And I'm going to talk about tree traversal coming up. And we have fewer, well, say less levels, sorry about the language, fewer levels to deal with. Okay, so what do I mean by balance? Splitting. Here we had, in the earlier example, remember I chose B as my node to put a hyperplane along, and this split A up into A1 and A2. Well, I didn't have to choose B. I could have chosen to hyperplane along A, which would have resulted in that. Okay, so if I put a hyperplane along A, it doesn't split the two. When I put it along B, it does. So it splits A. Okay, so we end up with 5 polygons going hyperplane along B, or 4 polygons if we didn't. Okay, that's a simple case. Imagine a much, much more complicated case where you've got lots and lots of splittings. Okay, so trying to choose a polygon which results in the fewest splittings is one method. How do we do this? Well, in practice, we check a sample of polygons from the virtual world or from the space that you're dealing with, and you count how many splittings will occur. And you simply choose the one with the fewest or minimum number of splittings. Okay, we can't check them all. Okay, n polygons will require n factorial checks. So if you've got 6 polygons, and in every step of your algorithm you want to check them all, you'd end up with 720 checks, 6 factorial. So if you had 20 polygons, factorials grow hugely. You'd have 2.43 times 10 to the 18 checks. So if it took you 1 microsecond, which is 1/1,000,000th of a second per check, it would take 77,000 years to generate the BSP tree. Okay. I don't know about you, but I don't want to wait for 77,000 years. So we can't check them all, which is why we only take a sample. In practice, we take around 5, a random sample of 5 polygons from your space. Why 5? Well, somebody with a lot of time on their hands did a study, okay, and this is what they came up with. So what we have here along the horizontal axis is the number of polygons which were selected for the sample size. So what they did is they had a virtual world, and they said, okay, if I only take a random sample of 1 polygon, generate the BSP tree, what happened is the number of polygons grew by 190%. Okay. If you took the random sample of 2 polygons from each space, it dropped down to 140. 3, just under 120, etc. So the more polygons you pick, the fewer splittings. But after a while, you know, you're starting to get a bit of random noise in here. So along here, you're not getting much more bang for your buck. You're not getting much more benefit. So after around about 5 polygons, there's no point in checking anymore. Okay, so a random sample of 5. By the way, when I say out 5, out of thousands. Okay, imagine how complicated modern computer games are. How many you've got millions of polygons. So you only take a sample. Okay. Balance versus unbalanced. Well, that means whether equal number of nodes in the left branches and the right branches. So on the left, we have a balanced tree. Okay, so there's 2, each node has got 2, or each parent node has got 2 child nodes. And on the right, we have unbalanced. So you can see this is sort of heavier, I don't know, more nodes on the left than on the right. So what you want is balanced. But what you also want is fewer splittings. Okay, so we want fewer splittings, but we want it more balanced. It's, you know, it's a trade-off. You have to sort of compromise. To balance a tree, we select a polygon with an equal number of front and back polygons, but that may result in more splittings. So there's a trade-off. And what we do is we, well, people who, imagine you're writing a computer game, you create the level, you create the world, you generate several trees and just pick the one which is closest with the least splittings and most balance as possible. Okay, this brings us on to visibility ordering. It's very nice. We can create a tree. Is it, life's wonderful, but what use is that tree? Okay, well, the BSP tree is used to determine the rendering order for Painter's algorithm. So starting at the furthest away, ending at the closest polygon. A BSP tree is independent of the viewpoint. So at no point during the generation of the BSP tree are we worried about where the camera is. Okay, it's independent. We don't have to worry about that. So there's only one BSP tree needs to be generated. Okay, and what we do is we traverse along our tree. Means we do a tree walk. And whether a node is front or back facing, okay, if we have a front facing nodes, so you take your viewpoint and you take your node and you think, is my node, or are the polygons in my node facing the viewer? Okay, so like front or back facing polygons. If a node is front facing, all polygons the other side of that node are going to be further away from it. So for example, if you're looking at this wall, okay, imagine you're in a virtual world, there's a hyperplane along this wall, you're front facing, this wall is front facing you, any polygon behind the wall is further away from this polygon. If it's the other way around, if this wall was back facing, all polygons in front of the wall are closer. So that's how we do it. Okay. So for example, here's my worked example from before. Let's say my viewer is at P. Okay, this is where your camera is, and we have these 5 nodes in our virtual world. We start at node C, so we start at the root node. Okay, is C front or back facing P? It's front facing. So what we do is we go back. Okay, so we check node C. If it's front facing, which it is, we go to the back subtree. So then we check node B. Is B front or back facing? If I was to draw an arrow from P to B, okay, would it hit the front or back face of it? Back face, yeah. So because it hits the back face, we go to the front node. We do the opposite. Is our node front facing? If it is, we go back. If it's back facing, we go front. So we get down to A1. Okay, so in this case, we get down to A1. A doesn't have any children. So that's our first node, which we render. And the rule is, as soon as we rendered a node, we immediately render its parent, or add its parent. So we get to a leaf node, add it, or plot it, or whatever. Then we immediately plot its parent node. So we plot A1, then we plot B. Then we go to the other subtree. And in this case, A2 is a leaf node, so we plot that. Okay. The rule is, as soon as we plot a node, we add its parent. But we've already added B, so we add the grandparent node C. Okay, so we've gone, C is front facing, so we go back. B is back facing, so we go front. We've reached a dead end. We've reached a leaf node. Add the leaf node, followed by its parent. Then we go to the other child node. Again, we've reached a leaf node. Add that node, followed by its parent. But its parent's already been added, so we add its parent. So we've added A1, B, A2, and then C. And then we go down the other subtree, and finally we add B. Add D. Okay. So this is sort of algorithm 7. It's what we call an in-order tree walk. Okay. In order means you do something, you take a node. Okay, so this is my function. Again, this is a recursive algorithm. The inputs are the node, the current node you're looking at, and the vertex list. Sorry, the polygon list, which is going to be the order of the polygons in the pages algorithm. Okay. If node is empty, then return list. This only ever happens once we've finished all of the BSP tree. Okay. Else, check the node. Is node front facing? If it is, restart the function, but with the right child node, i.e. the back. Okay. Once you've done all of the back subtree, you add the current node, in other words, its parent node, and then you go down the other one. I mean, presenting the algorithm in that way is actually harder than doing it sort of in real life. If it's front facing, if it's back facing, just do things in reverse order. Okay, so C is front facing. So if we got this is our viewing position here, C is front facing, so we move to the back node B. B is back facing, so we move to A1. A1 is a leaf node, so we add to the rendering list followed by its parent. So our current rendering list is polygon A1 and polygon B. And we move to the other subtree, which is A2. A2 is a leaf node, so we add to our rendering list. We've already added B, so we add B's parent, which is C. Okay, so A1 and B were already in the rendering list. Then we add A2 and C. So, okay. Then we move to D. D is a leaf node, so we add it. All nodes in that tree have now been added. So this is my final rendering list. So if you have a look at this one here, we add A1 first, then B, then A2, then C, then D. So we start furthest away and we end up closest. So at no point do I have to calculate any distances or anything like that. We're just walking around the tree. Right, if you turn over onto page 3 of your activity, what I've done is I've actually created a BSP tree for you for each of those levels. Okay, so for each of these levels, what I want you to do is determine the rendering list. Now, I've given you several points. So imagine you're playing a computer game, and this is the level which your character is in, or the camera is in, and you're in this room to start with. Using this BSP tree at the bottom, determine the rendering order for the polygons so that all hidden surfaces are removed. Okay, so we're going to use that in order tree walk. Okay, so for P walk 0, okay, our root node is EMQ. Is EMQ front or back facing P0? This is P0. This is EMQ down here. So this is going to have a normal vector facing that way. So we're looking, from the point of view of P0, we're looking at the back of EMQ. So therefore, we go to HP. So we start at EMQ. We're looking at the back of the EMQ, so we go to the front subspace. Remember, it's always the opposite. Are we looking at the front or back of HP? What do you reckon? Front or back? HP got a normal vector facing up. So if I was there looking at HP, I'm looking at the front of it. So HP, we're looking at the front, so we go to JN. because that's the back. Are we looking at the back or the front of JN? Anyone? Back. So therefore we go to the front. So we end up at KL. So what I'm going to do is I'm going to say, okay, I'm going to add node KL. That's going to be my first node. I group them, I put curly brackets around them because I could add, it doesn't matter what order I add K and L. I could add L, then K, or K, then L, doesn't matter. Now the rule is, once you've added a node, you immediately add the parent node. So we added KL, therefore we add JN. And we go to the other child. So we start at KL, add JN, we go to IO. IO happens to be a leaf node, so we add that. But as soon as we add a leaf node, we have to add a parent node. If we try and add JN, we've already done it. So then we add JN's parent, which is HP. Okay, so from the top, we went down here to KL, then up to JN, back to IO, then back up to HP. Now we go to FG. Now FG is a leaf node, so we add that. Okay. Once you add a leaf node, you add a parent node. That HP has already been added, so we go back up to ENQ. Okay, so where are we? EMQ. So we've already done all of this side. So we're now down to CS. Is CS front or back facing to P0? Front facing, so we go back. Then we go DR. We go DR. The rule is as soon as we add a leaf node, we add parent node to CS. And we go down the other tree, it leads us to ABT. Now look at the order. Okay, let's have a look at what polygons we started with, right? This is the order which we've done them. So we started down here, KL. So we render those two polygons first. Then JN, so those two. Then IO. Then HP, those two. Then FG. Okay. So we're started furthest away from P0. We're rendering, the order, rendering order means we have the correct order for hidden surface removal. Okay, so notice we end with ABT, which tends to be sort of closest to P0. Now, in doing so, if we were to program this, the only thing we need is a dot product to determine whether something's front or back. Everything else is just tree reversal. So as soon as you've generated the tree, it's very, very quick to generate the rendering order for your polygons. Well, what if in our game we walk along the corridor and we end up in the room at position P1? So I want you to do the same, but work out the rendering order if your point of view is switched to P1. I actually made a mistake going through mine. Okay, so if you're at P0, sorry, if you're at P1, so we start at the top with the MQ. Okay, so P1 is front-facing EMQ this time, so we go to the back subspace, so we go to CS. CS is back-facing, so we go ABT. Okay, so we do ABT, CS, and then DR, and then EMQ. So once you get used to it, you can actually do it quite quickly. So the hard bit is getting down to the leaf node. As soon as you've got a leaf node, add that, add its parent, go to the other one. If it's a leaf node, add that, try and add its parent, it's already been added, so we go to EMQ. And we go down the other one. So then we've got HP. Now HP is facing P1. So we go to JN. JN is facing away from P1, so we go to KL. So add KL, add its parent, go to the other subtree. IO is a lead node, add that, followed by its parent, but we've already added it, so we end at HP, then we end up at FG. So if you look at the order in which, from P1, which we've added, it's round here first, so ABT, CSDR, so we have that sort of space. Then we go to EMQ, and then we go down here, we have that space, and then we finally add that space. Okay, and what if we move to P2? You can do the same thing. So P2 is front facing EMQ to go back, CS back facing to go front, so ABT, CS, DR, EMQ. Okay, so now we're at HP. HP this time is back facing P2. So we go front. So we've got FG. Oh, getting a Q for some reason. FG followed by HP. Clearly brackets are starting to struggle. JN is front facing, so we go back to IO. Followed by JN, followed by KL. So using the same tree for all three positions, we've been able to generate the correct rendering order. So that's what happens in games. You move around the virtual world. Every time you move the camera, it goes through the BSP tree again using this walk to determine the correct rendering order. And these are just dot product calculations, so they're quick. Are there any sort of questions on that? Let's see how you get on if you turn over the page to that more complicated one. Okay, so I've very quickly done. I've done the one from P0. So kind of imagine you're sort of starting off a level. You're in this corridor up here. Okay, this is the BSP tree. It was different from the one we did before. Doesn't matter. Okay, it will still give you the correct rendering order if you've got the correct BSP tree. So we first look at JMB. Now JMB are these polygons here. Now they're facing P0. Okay, so I go to the back subspace. Then I look at PT, which is here. They're back facing P0, so I go front. So I'm at a leaf node, so I add QRS, followed by its parent PT, then go to OU. That's a leaf node, so add it, followed by its parent, so I have to bypass PT because I've already done it, so I'm at JNB. Then I'm at DHX, which is these three here. They're back facing to P0, so I go front. I'm at EM. EM is back facing P0, so that's P0, there's EM. So I go front, so I'm at W. I add W, followed by its parent EM, then I go to GK. GK is back facing, so I go front, so I go to IJ, followed by its parent GK, followed by FL. From FL, I'm going to go all the way back up to DHX. So I've already added GK and I've already added EM. So I go up to DHX, go to AA. AA is front facing, so go back to B2. B2 is front facing, so go back to Y2Z. Add Y2Z, add B2, add CY1. Back up to AA, and then back down to AB1. Okay. It's really easy once you know how, and you can start to get quite quick at it. Right, I think I'll give you a sort of 20-minute break. If you don't want the break, fine. Just you can stay and calculate the rendering orders for the P1, P2, P3 in here as well. Okay. So if you do bugger off and get a coffee, can you get back here by about 10:02?